Good morning. Thanks to the audience for joining this webinar. Thanks also to Professor Santiago Álvarez for accepting our invitation. Professor Santiago Álvarez is Emeritus Professor of Inorganic Chemistry at the University of Barcelona, where he has developed theoretical research on bonding, stereochemistry, and magnetic properties of transition metals compounds. He has made also relevant contributions to the application of continuous shape and symmetry measures to stereochemical studies and to the establishment of structure properties correlations. One of his lines of research has involved the extraction of chemical relevant information from structural databases, the most outstanding being the new sets of atomic covalent radii and of van der Waals radii, adopted as standards by the community and highly cited, and a coordination ability index for solvent and anions. He is a fellow of the Royal Society of Chemistry, a corresponding member of the Spanish Academy of Science, a member of the European Academy of Science, and a lifetime honorary member of the Israel Chemical Society. For me, and I hope for all of us, it is a pleasure to attend this conference. And today, I hope to learn a lot from the speaker. Before I leave you with the talk, let me remind you that if you have any questions, use the chat and I will address the question to the speaker at the end of the talk. Please provide your name and affiliation so we can properly address questions. Your word, Santiago.
Good morning. Thanks to the group of crystallography and crystal growth of the Spanish Chemical Society and Physical Society for inviting me to giving this webinar. And thanks to all of you who are connected to attend this lecture. Let me probably better share my screen. So if I can find it now. We have tried earlier, but now I can find where's the button to share my screen.
Parte central en la barra inferior.
Oh, thanks. Thanks, Pilar. Now, do you get it? Is it all right?
Yes, perfect.
Okay, so let me start. Yes, I'm showing you here an old Mappa Mundi because we are talking about the world of molecules and how the molecules are distributed in a crystal or in a solution, mostly in a crystal, and how in these regions of a crystal, the molecules can pack together and form populations, different populations, and can interact in different ways among them. Some are very far away from each other and doesn't usually meet. Some people are always together or very commonly together, so they have strong links. And this is how I like to see this world of interactions between molecules, the world of intermolecular or non-covalent interactions in which we are lately, have been lately interested, or for many years, I would say, but from different point of view. So, as Roald Hoffmann said in one of his nice poems, men and women are not as different from molecules as they think. So I tend to think of people who study the interactions between molecules as molecular sociologists. And using a map, so we will be probably also geography. So we are doing with molecules something that we do with human organizations like countries and the relationship between men and women. This talk will comprise several topics, that have to do with this territory of van der Waals, territory in which the molecules are not so strongly linked together, but show some tendency to attract each other, what we usually call non-covalent interactions. And so that will cover a few years of work, including our recent thoughts that will come in the last point of the talk. So essentially, I will talk about 4 points. I will skip the third one to avoid making the talk too long. First, structural cartography, or how we describe the distribution of different atom pairs in a crystal. Then shape analysis, how using the continuous shape measures we have extensively used in the last 20 years. We can also take a different look and get interesting information for complexes or molecules with weakly coordinated fragments or ligands. Then I will also talk a little bit about our studies, theoretical studies on the alkane-alkane interactions, so one of the weakest probably intermolecular interactions, but it can be strengthened by different means. And that can also teach us something about these weak interactions. And finally, I will try to introduce the idea of the van der Waals crust and how this definition of a van der Waals crust can be of help in analyzing structural data, be it experimental from X-ray structures or theoretical from quantum chemical calculations. So let's go to the structural cartography first. Let's start with an example of how we deal with hundreds of thousands of structural data. I would say millions. We deal with more than 1 million crystal ray structures nowadays. And in each crystal structure, there are hundreds or maybe thousands of interatomic distances. So if we have these aluminum compounds, which the aluminum atoms are depicted in light blue, oxygen atoms in red, and then carbon atoms and hydrogen atoms. And if we look at the aluminum-oxygen interactions, these atom pairs, aluminum and oxygen, we can find, for instance, bonding interactions, like between this aluminum atom here and this oxygen atom here, because they are very close distance. We call that a chemical bond. But we can find also longer aluminum-oxygen distances, which can be, for instance, intramolecular contacts, like between these two atoms, aluminum and oxygen, which are non-bonded. That is, they have a longer distance than these two atoms here. Or we can also find intermolecular contacts as between the same aluminum atom and this oxygen atom, which belongs to a different molecule. So these are essentially the 3 types. We will see that there are maybe more sometimes, the 3 types of atom-atom distances that we will find between 2 different elements in a crystal structure. And we can do that for one after another structure and get information for this society of molecules that are the crystals. So this is what we get if we look at the aluminum-oxygen distances in the Cambridge Structural Database. That was made a few years ago, but I'm sure this will not change very much if we do that today. First, we find this peak here, dark gray, which corresponds to aluminum-oxygen bonds. You see that the covalent radius of radii of aluminum-oxygen gives a sum of 1.87 angstroms. So we expect that an aluminum-oxygen bond would be around that distance. And we find a peak, a very strong peak with more than 3,000 structures at around the distance, somewhat below 2 angstroms. So those are thousands of aluminum-oxygen bonds in many, many different structures of chemical compounds. But then we have intermolecular contacts, those non-bonded distances between an aluminum and an oxygen atoms within the same molecule. And this is what we get. All distances are longer than bonds, of course, And you have a peak here, and then a more or less continuous distribution as we go to longer distances. And we can still have intermolecular contacts. We can distinguish very easily when analyzing the database which distances between aluminum and oxygen are within a molecule and which ones are between different molecules. And this is what we get for intermolecular. Again, we have a peak here at around 4 angstroms, and then an increasing number of distances as we go to longer values of the distance. So if we put all the information together, this is what we see. The bonds, the intermolecular non-bonded distances, and the intermolecular non-bonded distances. And we can see different aspects of this plot. For instance, you can see that there's a clear gap between bonds and non-bonds. This is by just the distance, we can very easily decide whether an aluminum and an oxygen atoms are forming a chemical bond or not, just by the distance. This is not always so. This is not always the case. Then we find the intermolecular peak of non-bonded distances at around 4 angstroms and the intermolecular peak at about the same distance. So that may mean something. And then we find more distances or more pairs of atoms at longer distances, which are away from this peak, from this maximum here. This corresponds simply to the random distribution of atoms around a central molecule. You take some aluminum atoms in this structure, in a particular structure, and you look at all the oxygen atoms around it. Within a molecule, you go easily off because the molecule is finished, and there you have no more contacts beyond such distance. But for intermolecular distances, as you increase the distance or the radius of the sphere around the aluminum atoms around which you are looking for oxygen atoms, the probabilities of finding oxygen atoms increase with the volume of the sphere, that is with the cube of the radius of the sphere. So that's why you get such an increase. This is just by random distribution. It has nothing to do with having an interaction between an oxygen atoms here at 8 angstroms from our aluminum atom. And this peak here is what we understand that describes the concentration of interactions, weak interactions between molecules. So this is what we call the van der Waals region. So notice especially that this is a region, not just a value. So we have many different distances that may have the same meaning. That is, an oxygen atom is weakly interacting with an aluminum atom. So these are convenient maps, but we will disregard intramolecular contacts, except if we are very interested in particular case of intramolecular interactions. But we are looking at the weak intermolecular interactions. So we disregard in the next few slides these intramolecular contacts. And in top of the contact or non-bonded aluminum oxygen distances or 2-element distances, we also plot the bond distances because that gives us a reference. So we will have something like this, omitting the pink, the violet part of this plot. Well, we not always find such a clear-cut distribution of distances. Sometimes we have some odd distributions. This is the case of lanthanum and oxygen. If we look at pairs of atoms, of lanthanum and oxygen atoms, we find first, I insist, the blue color here means intermolecular contacts. We use the gray or black for bonds. So we find a lot of pairs of atoms at short distances, which are considered as contacts. And then we have sort of a gap, some structure, a few of them. And then we have, again, a peak at long distances, the van der Waals peak, and then the random distribution that goes up as we increase the distance or we increase the volume of the sphere at which we are looking for the oxygen atoms. So what happens here? Why do we have these short distances that are below the van der Waals peak? Well, if we plot now the bond distances, lanthanum-oxygen bond distances, we find that there's a perfect superposition of the two peaks. So what does that mean? That means that the intermolecular contacts at such short distances are just undisclosed bond distances. So when the structure was coded into the database, the crystal structure the description did not include these distances as bonds, but they are. Okay, we can do an exercise. Since this was on some years, 8 years ago, we can repeat the same plot today with the structural information at the Cambridge database, and this is what we find. Now this peak of intermolecular short distances have diminished a lot. And that's why simply the codification of distance or pairs of atoms, of lanthanum and oxygen, as being bonded has improved. So there are still a few undisclosed bond distances, but so whenever we find such short distances, we may suspect that there are bonds which have not been detected or disclosed. And we have the van der Waals peak, of course, very, very clear. Here we have another case. That's for the lithium-lithium distances. It can be the same element, contacts between atoms of the same element. And this is what we find for intermolecular distances. No short distance apparently, but well, if you look at the bonds now, this black histogram here, you see that some of the distances here correspond to the intermolecular contacts. So again, we find that the definition of what is or what is not a bond is sometimes dubious. So we have to be very careful not to assign a bond or a distance as being bonding or non-bonding by just the value of the distance. We have to look at it in a wider context and see what happens with a wide distribution of distances in many, many crystal structures. Okay, that's another thing. If we consider this peak here to represent the lithium-lithium bonds, what happens with this here? Are these contacts, are these random distribution of van der Waals contacts? There's no real gap here. There's a minimum, of course, but there's no real separation between bond and non-bond. So that's one characteristic that may appear quite often, that for some atom pairs, it's not easy to tell when, at which distance we don't have no longer a bond and when we start to have an intermolecular contact. Okay. Another added complexity we can find in the distribution of atom-atom distances is the presence of oxygen, or sorry, hydrogen bonding. If we look, for instance, at contacts between two oxygen atoms, we find something like this. Bond distances, as usual here, very well separated from intermolecular distances. But here I am showing two different representations at the right. One is the representation of contacts between two oxygen atoms in which there's also a hydrogen atom that may be forming a hydrogen bond. And you see that there's a peak here. And in blue, you have the distribution of pairs of oxygen atoms that do not have the possibility of a hydrogen bonding. No hydrogen atoms attached to them. And you see that here the peak has moved to the right. So we can interpret that this peak here corresponds to the distances between two oxygen atoms that are close together because of the existence of a hydrogen bond. And we have another peak here that is due to another kind of attractive interaction, van der Waals or whatever non-covalent interactions that appear at a somewhat longer distance. Okay, so if we are careful enough when we do the analysis, we can separate the two types of interactions and distinguish hydrogen bonding from van der Waals or other non-covalent interactions. So we have the hydrogen bond peak. We disregard the hydroxyl groups, and then we have the van der Waals peak. If we look now for other atoms that may have hydrogen bonds, for instance, nitrogen, oxygen, and nitrogen pairs, this is what we find. For nitrogen, we find again a clear peak of hydrogen bonded atom pairs, but we don't see a peak of van der Waals interactions. We look for now nitrogen-nitrogen interactions. Bonds, now hydrogen bonded species, not that many, but a clear peak. And there may be a peak here. We just see a hump that could be of van der Waals interactions, but not so clear. If you go to nitrogen-nitrogen without hydrogens, with some restrictions, then you can see something that looks better, like suggests that there is a peak here. So that's something that we will be able to handle in a moment. So how we can detect whether or not there is a peak here. So this is a problem that we may face in the future. Here it's very, very doubtful that we have a peak, but who knows? There's some inflection, apparently here. Well, there is a third case when we have weak bonds that we call them chemical bonds, but are longer than usual. And this happens very often in copper. People who is familiar with transition metal chemistry knows that copper in oxidation state +2, when its 6 coordinates has formed 6 bonds, have the so-called Jahn-Teller effect. It's an electronic force that makes the molecule distort, so 2 of the bonds are longer than the other 4. That's for electronic reasons, we're very well understood today, and that makes you have a wide range of copper-oxygen distances that are bonding, but not so concentrated as in other cases. So let me show you the histogram of the distribution of copper-oxygen distances that we get from crystal structures. So we find first a peak here at short distances, 2.0 angstroms. Then we have sort of another peak or a decrease of that peak, whatever you may consider this. And then we have a quasi-gap. And again, now we have a van der Waals peak and the random distribution function of atom pair distances at long separations. So how we can interpret this region here? Well, first we have the bond distances between copper and oxygen, both copper 1 and copper 2. See that the distances are not that different. They may be different if you go to the third decimal figure or even the second sometimes, but in a wide perspective, they are not that different. But then we have this second peak that corresponds to the long or Jahn-Teller copper 2 oxygen bonds. And why we know that? Because if we remove from our structural set those thousands and thousands of molecules, those that contain copper 2 6 coordinated, where we have these weak bonds, this peak disappears. So this peak here corresponds to the Jahn-Teller elongated copper oxygen bonds. And then we have the van der Waals peak, and let me observe the observation that we don't have a real gap between the bonding and non-bonding regions. So this is one of the cases in which bonding and non-bonding have a smooth border, not very well defined frontiers. So can we distinguish bonds from contacts? We will see how we can do that. Not always. The first idea is that not always we can distinguish them. And in this case, we can consider only 6 coordinated copper to look at intermolecular contacts. So then we get this. If we consider all the copper-oxygen contacts, those were included here, everything was included here, bonds and non-bonds. Now we separate bonds, copper-oxygen bonds, all copper-oxygen contacts, you have no gap, continuous distribution of copper-oxygen pairs. And if you look only at 6 coordinated copper-oxygen, then whatever additional copper-oxygen distance does not correspond to a bond, because copper doesn't usually give higher coordination numbers than 6. So mostly 6 coordination or lower coordination numbers. And then now you recover the gap. So the gap is due to the lack of frontier or definite frontier between bonds and non-bonds only when you have copper to weak John Taylor elongated bonds correspond to this distribution of distances here. Okay, so now we recover van der Waals swap, and now trying to recap all what I said so far, I can make a generalized or schematic map of what we will find essentially when we look at atom pair distances. That's for a given distance between the given pair of atoms or pair of elements, we will find first at short distances a distribution of bonding distances. Then we may have a van der Waals gap, if we are lucky, then a van der Waals peak, well separated from the increase of random distribution. Not always so well separated, but in principle, this is the ideal scheme we should expect when looking at all distances between two different atoms. Okay, now, how can we describe in a more quantitative way this region or this distribution, the van der Waals region? I mean, forget about this peak, which is the bonding region. Now look at the van der Waals and random distribution regions, which sometimes may overlap. You can see that this function here would continue over here. So in this region, we have the superposition of two types of distances, those that correspond to van der Waals interactions and those that are there just by random distribution. So then we can assign for these peaks here a function like this one. Just don't worry about the details. It's very simple. You just have two terms. One term, the first term, tries to describe the van der Waals region. That's a Gaussian distribution. It's very easy, very nice, very symmetric. And we have a function of the distance, so we represent the number of atom pairs that we will find at a given distance as a function of the distance. And then we have some parameters that we can fit if we have many structural data. And then we have a second term in this equation that corresponds to the random distribution. Since in a sphere, the number of molecules that you will find close to a given molecule increases with the radius of the molecule, as in the pomegranate, the neighboring seeds are increasing, or the number of seeds at a given distance from the center, for instance, are increasing with the cube of the radius. As you increase the radius, then we can describe this distribution by a simple expression, such as this one here in the right of our equation. Let me go back to this. Just to tell you that the parameters have some meaning, these parameters in this equation here. So D max here gives you the distance at which appears the maximum of this peak. Sigma gives you the width at half width of the peak. So sigma is related to the width of this peak. And then you have, we will talk later about the van der Waals radius or the van der Waals distance. And in the second term, as I told you, the random distribution function, which has only two parameters. D0 is the threshold distance, starting from which we start to have some random distribution or random appearance of atom pairs, which need not be at the very beginning here, maybe a little farther away, but that doesn't matter. It's some point somewhere here that represents the 0 for this function here. And then you have A and B that represent the relative proportions of contacting molecules and non-contacting molecules. That's all, okay? So if we are able to fit the histograms I have been showing to you before to this function, we can have these parameters get some physical, semi-quantitative, at least meaning for these parameters. So let's take as an example rhodium-oxygen pairs, and this is what we get for the intermolecular contacts in blue. You can see that there's a hump here, maybe there's a peak. So we can fit by this equation, this distribution here as a Gaussian here that overlaps with the random distribution function, the cubic function. And we can deconvolute this and represent them separately. And this is what you have. You have this distribution of van der Waals distances and this distribution of random distances. So at a given distance within this van der Waals region, we may have both. For instance, in this case, here you have this amount of atom pairs that correspond to van der Waals according to this separation of this function, and all the rest are distances that should appear by just random distribution, because that's what's telling you all this curve here, which is also fitted for these distances. Okay, so you see that we have a region in which we call van der Waals, in which they are van der Waals distances, but also some distances that appear there are just at random. And we can calibrate, how can we calibrate the reliability of this, of the whatever data we get from this van der Waals peak here of the Gaussian distribution? We will see in a moment. If here, for instance, we get this data, whatever they mean, we get the maximum of the van der Waals peak, which is here, not here. It's a little shift between the maximum that we observe and the maximum of the Gaussian distribution. And you have two parameters, give the relative weight of the two terms of the equation, and the width of this Gaussian here, and the threshold to 2.55 Armstrongs. So this curve here vanishes at 2.55 Armstrongs. Now, told you about reliability of this description of the van der Waals region. So we can define the ratio of van der Waals or molecules within the, or atom pairs, sorry, within the van der Waals Gaussian peak and those that appear just by random. That's our reliability index will be the number of van der Waals contacts divided by the total number of contacts at the distance corresponding to the maximum of the peak. Okay, if we would do that, we will see that here the random distribution function that can be deduced from the previous equation and can be obtained by just using the fitting parameters that we obtained. In this case, the calculation gives us that this curve here has a reliability index of 54%. So that is by just looking at the distance. If we have an atom pair at this distance, we have a probability of a 54% that that distance is due just to van der Waals interaction and not by random distribution. Of course, we can look in a particular case at the chemical or geometrical features of the molecules, and we can deduce whether or not this corresponds to some kind of interaction or not. But we have better situation in other cases. For instance, we change rhodium by osmium, look at the distances with oxygen, we get this distribution here. We can fit this to our equation, and we get a reliability index of 90%. So that's something that can give you also an idea of how good are your data. Okay, it's taking longer than I expected, so I will have little time for the rest of the topics, but let me try to move forward. This distance here is what we take as the van der Waals distance between the given atom pair. Between atom E and atom X, for instance, in this example, the distance here at half width of the van der Waals peak is what we call the van der Waals distance. So if we know the van der Waals radius of one atom, we can subtract and obtain from this enormous amount of experimental data the van der Waals radius of the other element. So we have what we did some time was to take oxygen as a reference, because oxygen is present in a large proportion of the crystal structure we know, and there are bonds and contacts for most elements in the periodic table to oxygen. And we obtain, for instance, for the oxygen-oxygen distance, this distribution here, and we obtain a radius or a van der Waals distance of 3.25 angstroms for the peak, the maximum. But this distance here is not that one of the maximum. This distance here, the van der Waals distance is 3.0 angstroms. So half that distance, 1.50 angstroms, is the van der Waals radius of oxygen. And that's what we take as a reference. Okay, we have thousands and thousands of data. So this is a number that is representative of many, many thousands of experimental crystal data. Of course, with some uncertainty. We have some width here that tells you that this is not just a value, but this is a region. And this is comparable to the van der Waals radii or radius for oxygen that were used earlier. The most famous ones are those of Bondi, but they were available only for a few main group elements in the periodic table, so where they had some limitations. See this, they are practically identical, and also another radius used by Sanovo's 1.55. So starting from that, we did analysis of all elements that we could. Not all elements have compounds enough to obtain this van der Waals radii, and this is what we obtained, and then we deduce the van der Waals radii of some 92, I think, elements of the periodic table. And some of them with different reliability. You see the well-defined peaks are those that, or the well-defined radii are those that appear in boldface, and those that are poorly defined appear in italics. But overall, you have a general perspective of what are the van der Waals radii. In fact, these are the distances, not the peaks. Okay. For the distances, you have to detract the value of the radius of oxygen, and then we can plot this as a periodic function of the atomic number, and you obtain a very nice periodic distribution of van der Waals distances, or atomic size, if you wish, with maxima for the alkaline elements and minima for the halides and the noble gases. Of course, there are some strange things and some trends that can be analyzed in detail, but I will not go further onto that. I will only tell you that by looking at the rough picture, the wide number of data we have analyzed, more or less you can say that the van der Waals distance is at 0.3 angstrom lower than the maximum of the van der Waals peak, and the minimum of the van der Waals peaks at the right is some 0.4 angstroms from the maximum. So overall, you can expect van der Waals contacts between the van der Waals radii sum and the van der Waals radii sum plus 0.7 angstroms. And similarly for the left side of the peak. So you can find van der Waals contacts between the van der Waals radii sum and 0.7 angstroms less. But this is just a rule of thumb, and then the gaps can be of different widths. They range between 0.2 and 1.6 angstroms. So a rule of thumb is that a value of 0.7 angstroms, of a distance of 0.7 angstroms between two atoms, more or less than the sum of van der Waals radii, may indicate the existence of some van der Waals interaction or weak covalent interaction. this arrow here, and similarly for the chemical bonds, and I will not go further into that. We have checked that as we deduce all the radii from just element oxygen pairs, if we take, for instance, sulfur. So how do we deduce, how do we predict the sulfur-sulfur distances? So we have analyzed a variety of combinations, and you see that this is what we predict. This arrow here indicates that 2 times the van der Waals radius of sulfur would make you expect this range of distances, and this is what you obtain actually, this distribution that is in good agreement with the sum of the van der Waals radii of 2 sulfur atoms, and similarly for other atoms, for instance, gallium and nitrogen. So let me move to a shape analysis. Try to skip some details, but the idea is that in the crystal structures, you have seen that there are many cases, or some cases at least, in which there's a continuous distribution of atom pairs between clearly bonded and clearly non-bonded atoms. And this happens, for instance, for titanium. If you look at the barium titanate, you can see that this titanium is in a tetrahedral environment, has 4 bonds to oxygen atoms with an average distance of 1.8 angstroms, whatever it means. If you go to rutile, same metal, titanium, same atoms bonded to it, oxygen atoms, same oxidation state for titanium, titanium 4, then it's octahedral. It has 6 bonds, and the distances are a little longer, as we expect when the coordination number increases, 1.96 angstroms. But if you look at another polymorphic form of titanium dioxide, anatase, then the structure around titanium is a little different. Then you have 4 short distances that are somewhat planarized tetrahedrons. We go from a tetrahedron here to a planar distribution of these 4 atoms here, where this is the intermediate geometry. And then you have longer distances between the titanium and these 2 atoms. So in some way, what we are doing is we are approaching 2 oxygen atoms from top and bottom of the titanate anion. We are forming this anatase structure with intermediate distances for the 2 approaching oxygen atoms. And then finally, we form a 6-coordinate compound with 6 identical titanium oxygen distances. So this represents, or this structure here represents a snapshot of the process of forming 2 more bonds to this titanium cation. Well, so we studied a variety of situations in which you have this problem, that you have distances that are intermediate between bonding and non-bonding that could be described as being along the path of formation of more bonds, or let's say to ligand association or ligand dissociation. And the existence of ill-coordination numbers, ill-defined coordination numbers. That reminds us of the snapshots that Etienne Jules Barré reported in 1883 to show the motion of man walking, or what also Edward Muybridge did at almost the same time. It was by taking different pictures showing snapshots of the motion of a galloping horse. So for this analysis, we use shape measures. Making a long story short, we define the shape measure of problem structure or problem geometry A related to the ideal geometry A. So we wish to compare this figure here in blue with the regular, very symmetric square in red, and the shape measure or is given by this expression that has to do with distances between these atoms when you have the 2 structures superimposed, and this value or this variable, this shape measure, can take values from 0 to 100. This is 100 here. So if this shape measure is 0, that means that the two structures are identical. So our structure has the most perfect form that we imagine, the one we use as reference. If the value is higher than 0, or it gets higher than 1 or 10 or 100, then that means the distortion is quantitatively higher. So we have a measure of calibrating, a way of calibrating how distorted is this molecule with respect to the ideal shape. Then we do some more things. For instance, we calculate or we compare the geometries of compounds formed by metal atom and 6 radicals or metal anions or any kind of ligands. And we analyze their shapes relative to the octahedron. So this is a measure relative to the octahedron. And we find in these families some structures that give a value of 0. That means they are perfect octahedra. And then at the same time, we use in this plot the measure relative to the trigonal prism here. And when you have the octahedron, the distance or the shape measure relative to the prism is more than 15, some 16 something. But you find other structures that have values of shape measures higher than 0 relative to the octahedron, and then smaller values relative to the trigonal prism. That is, they are being distorted in this a way that is called the Bylar twist, that is rotating two trigonal faces of the octahedron relative to each other to reach finally a trigonal prism. And we find more and more structures that are distributed along this path. Finally, some of them are perfect or nearly perfect trigonal prisms and are very low distance from the octahedron, shape measure of 16 again, and some that are intermediate. So that we call this shape map, in which you represent the geometry of a given compound relative to two regular shapes, and that gives you some indication of how you are in between two regular structures. I will not describe all of these mathematics that tell you how to describe these paths, but I will tell you that we can compare, for instance, two structures like the ones we saw for titanium, the tetrahedron and the octahedron, because they have this common fragment, a metal of 2 or 4 ligands. And in this case, we can get this parameter here that describes the position of the structure along the path. So 0 would be a perfectly tetrahedral. Here we have titanate, which is 4% along the path, anatase 34%, this molecule with alkoxide 79%, and rutile 100% octahedral. So you can describe quantitatively this path, and then you can analyze other pathways like the addition of 2 ligands to a square planar complex to finally give an octahedral complex. We look at this, in this case, for nickel compounds, nickel 2 compounds, and you find that there are many described in the database as being square planar, 4 coordinated, that are here close to the square planar, that is trans-dissociated octahedron, or many that are described as being octahedral that appear here. But some of the ones that are described as 4 coordinated, in fact, are closer to the octahedron. So you can find a wide distribution of structures that are intermediate between the square, just 4 ligands, or the octahedron, 6 ligands. So even the coordination number can be not so precise a number in some cases. Okay, so and we have done that for different cases, octahedron to capped octahedron, and octahedron to a pentagonal bipyramid with specific ligands, and we can see how we find many structures that cannot be described as only being octahedral or only being capped octahedral, but many of them are intermediate, and we can use the shape measures to analyze them. This is a table showing all the paths that we have analyzed. So you can see many different geometries and many different compounds that can be found with those intermediate geometries. And I told you I was going to skip this. Sorry. I have to remove the last laser. Oh, okay, let's go in a different way. Let me skip that because I'm over time. And now tell you that we have looked at these intermolecular contacts, which are very weak between alkanes. And sorry, but I'd rather spare you of this, and maybe some other day I will have a chance to explain you about how we found how can you influence the strength of these interactions just by increasing the number of carbon atoms attached to the CH groups that are forming these weak interactions, or by increasing the or decreasing the bond angles around these carbon-hydrogen fragments. And to end, I will just briefly tell you about the van der Waals crust. Vicente or Pilar, may I still go for 3 or 4 minutes, or I maybe stop here? Well, if you say nothing, I understand that I can just use 2 or 3 minutes.
Yes, of course.
Thanks. Yes, we have 2 different atoms. They are spherical, why not? And we have the covalent radius of these atoms, R, that defines a sphere. And we have the van der Waals radius for that atom, we define with V, this letter here. So the difference between the 2 radii, we call W, is the van der Waals crust. So you can imagine this sphere of the valence electrons, the high electron density of the valence shell of the atom, that is surrounded by a crust of much lesser electronic density that corresponds or even the potential, electrostatic potential surfaces that may interact with neighboring atoms. And then here you have another atom in contact with his own atomic radius, covalent radius, his van der Waals radius, and his cross with a different width, we call WB. And the distance between the 2 atoms, defined by the distance between the centers of the 2 spheres, will be D. Okay? So these are the parameters we use, very well known, radii, and now we just make a difference of the radii and we get the width of the crust. And what happens when we start interpenetrating the 2 crusts? Well, we go from here, we have just the 2 atoms in contact, then this will be, the distance will be the sum of the van der Waals radii. So here, or distances slightly shorter or longer, we would say there's a van der Waals contact. So the distance equal to the van der Waals radii, or the cross of the 2 spheres being just in touch without interpenetration, is what we call van der Waals contact. If we go to a shorter distance, now the 2 crusts start to interpenetrate. So the interaction between the van der Waals region of each atom interact more strongly, and we have some interpretation of the width. So the distance is smaller than the sum of the van der Waals radii, but still longer than the sum of the atomic radii. So there's no interaction between the valence shells of the 2 atoms, no bonding, no really covalent bonding. And we find finally, we can find the 2 atoms at the contact distance between the 2 valence shells. That's the distance will be the sum of the covalent radii. We would say that there's a chemical bond there. And then we can go further and interpenetrate even the valence shells, get stronger bonds like double or triple bonds, why not? Okay, so this is the idea of the van der Waals cross and how we can use it. So we can just define a very simple parameter, that's the van der Waals or interpenetration index or penetration index. That's the sum of the van der Waals radii minus DAB, so how much the distance between the two atoms is smaller than this, the sum of the van der Waals radii, how much the two spheres interpenetrate, but we take a relative value that is divided by the width of the crusts, by the addition of the widths of the two crusts. And we multiply this by 100 to have a percentage. And this is 0% then. This is some penetration index smaller than 100%, but larger than 0%. That is positive value. We have 100% when the two valence shells are engulfed, or we have the distance equal to the sum of the covalent radii, or we can have values larger than 100% when we have stronger bonds. Of course, we may get negative values to the left if we have the two atoms separated at least the distances a little longer or strongly longer to the van der Waals radii sum. So it doesn't know. But the percentage has a lot of meaning when you have these situations here, when you are approaching the two atoms within the van der Waals crust, not getting into bonds and not going too far away. And just two simple examples of how you move. You can use this idea. Hydrogen-hydrogen interactions that I was going to talk to you about, but didn't have the time. We have calculated for different alkyl groups these interactions between two hydrogen atoms, and you have here the optimized distances for this interaction with distances and the energy values, very small energy for this interaction, attractive energy, of course, negative, they're attractive. And we see that if we plot the dissociation energy of these pairs of alkane molecules against the hydrogen-hydrogen distance, we get a plot like this. That means the atoms are far away, the interaction energy is small, the dissociation energy here is very small. As they approach each other, the interaction energy decreases. That's, everyone can understand that. We don't need much more information to understand that. But if you plot the same thing as a function of the penetration index, you have essentially the same, because now the positive penetrations indicate shorter distances. So we are inverting the two plots, the plot. We have the same, essentially the same, but now we have different values in the abscissa axis. And you have a reference value here of 0. That means that for larger penetrations, you have stronger interactions. For weaker, for negative penetration indices, we have weaker interactions. And this is the interaction at the typical van der Waals distance. Okay, okay, that's one thing. We can compare also other types of atom pairs, not essentially the same element, but two different elements. And just one example here that comes from a work published by David Casanova and others. It was inspired at the same time by Lee Brammer, a nice structural correlation study published in 2000, in which he analyzed the interaction between alkyl ammonium cations and cobalt carbonylate anions, and found that he could describe the proton transfer between the ammonium cation to the cobaltate anion as a proton transfer reaction by just looking at crystal structures, the different compounds that show different stages of this process. In this process, you are breaking nitrogen-hydrogen bond and you are forming a cobalt-hydrogen bond. So let's represent how we calculated the energy of interaction of these two fragments as a function of the penetration index. So you start from a low penetration index, then you have an ion pair here. The minimum, in which you have a clear cation with nitrogen-hydrogen bond distance, but cobalt-hydrogen distance that is short enough. You see, you have 75% of penetration of the van der Waals cross of hydrogen and cobalt. So it means something is happening there. It's not close to 100%, but it's a pretty high interpenetration of the two crusts of van der Waals. And if you continue increasing the penetration, these points are here are the actual calculations. The red points indicate the stationary points in the potential energy surface. It's a minima or a maximum. Then you reach this maximum, which is transition state. So the highest energy, the transition state, is at 95% of penetration. You are almost formed the cobalt-hydrogen bond, not yet broken the nitrogen bond. And then from there on, as you increase the penetration now, you go to 100%, 103 in this case, and the nitrogen-hydrogen bond starts to break. And you finally get this atom pair, which may have some hydrogen bonding. So that's what you may have the nitrogen at not such a long distance, still some penetration. So this is what you'll see if you now plot the two penetrations. Cobalt-hydrogen penetration index is increasing here because that's what we impose in our curve, even if we find minima at 2 points. And then the nitrogen-hydrogen penetration index. So at the beginning, you have practically 100% penetration between nitrogen and hydrogen and H bond. You start forming hydrogen-cobalt bond, so you increase the penetration, and nothing changes that much, just a little bit of elongation of nitrogen-hydrogen, decrease the penetration. You reach the transition state, now you start pulling away the hydrogen from the nitrogen, so that requires energy. But once you have passed the transition state, now the attraction of the cobalt is doing its job, and now as you increase the penetration of the cobalt van der Waals crust, you are getting away from the van der Waals crust of nitrogen, and the nitrogen-hydrogen penetration index reaches 40%. As I told you, just 40%, not less, because there's still some interpenetration. Why? Because you have hydrogen bonding between nitrogen and this hydrogen. So you have two different bonding situations, an ion pair, a hydrogen bonded pair of molecules, which pass to into intermediates, which are representing the process of hydrogen or proton transfer. Sorry. And well, these are the actual values of penetration indices. These are the experimental values where you can see how these structures give you this situation which is intermediate, or how can you can force chemically an intermediate situation which is close to the transition state, and finally when you have transferred the hydrogen or the proton to the cobalt. And with that, I will just like to show you how you can classify many different types of non-covalent interactions by just looking at the ranges of penetration indices they show, and how you can go use that also for covalent bonds. For instance, you can see here carbon-carbon bonds at the bottom, these spheres here, that's the single carbon-carbon bonds, 100%. That's experimental data on the Cambridge database. Carbon-carbon double bonds, carbon-carbon triple bonds. If you look at chromium-chromium bonds, single, double, triple, quadruple, and quintuple. And with that, I finish. I apologize for being over time, and I thank you for your attention.
Thank you very much, Professor Álvarez, and for your talk and for your huge job. We have two questions. The first is from Jose Conesa, and he says, "Dear Professor Álvarez, there was a slide which involved two oxide copper. Oxide copper 2 is actually distorted due to Jan-Teller effect, but copper oxide 1 has, as far as I know, a purely tetrahedral structure, and then a random distribution of copper oxide contacts. However, for the two cases you saw seemingly was the van der Waals interaction. Is this correct?
Yes. Nice to greet you, Jose Carlos. Hope you're fine. You are right. I don't distinguish between oxidation states when I look at the van der Waals distances because it doesn't involve the essentially valence electrons or them being paired or unpaired. But for covalent bonds, that has a small problem that you know that the distances, sorry, the distances depend on the oxidation state, may change a little, but within the accuracy that we are using for atomic radii, that's not very important. In the case of copper 2, copper 1, the main problem is in the existence of the Jantler effect for copper 2 that gives you such a variety of long distances. But I haven't separated the intermolecular or long distances between copper 2 and copper 1. So I cannot tell you exactly how much of those contacts come from copper 1, which ones come from copper 2. That can be done. It requires some work because not always the oxidation state is very well coded in the database, but that can be done. If you are interested in looking at the difference between contacts of copper 1 or copper 2, that could be done. But in principle, we just focus on an element disregarding oxidation state and even coordination number, except for those cases, as in copper, in which that could mean a significant difference in chemical bonding behavior. Hope I answered your question, Carlos.
Thank you. And another one from Ramon Bosque from the Universitat de Barcelona. Thank you for the talk. I have one question. Why do you take dW at the half width of the van der Waals peak and not at the maximum?
Yeah, that's a conventional definition of the van der Waals radius. It's not me who made this definition. I just have followed the rule and to be consistent with what has been used in the literature, the chemical literature for so many decades. I think we should use a consistent definition of the van der Waals radius.
And I think no more questions. No more questions? Okay, thank you very much, Professor Álvarez.
Thank you for your invitation and thanks to all of the attendees for being here.
Thank you very much. It was really very, very interesting, your talk, and we hope to see you in some of our meeting of crystallography.
Nice.
Then there is not more question.
And another is not a question, is congratulations from Elías Molins. Enhorabuena por la iniciativa. Thank you, Elías.
I join Elias in congratulating you for your initiative.
Okay, then perhaps it's little later, then people have some thing to do. Then we finish here the session, and well, we hope to meet you another time in other of this session. Thank you very much.
Bye bye. Thank you.
Thank you, Santiago. Y nada, encantada, ha sido realmente muy interesante. Es muy